Okay, right. So today we are going to discuss organic chemistry. Right. So in this, we'll see only the important points or the important topics which we may expect to come in the exam. So first of all, what is organic chemistry? So organic chemistry is nothing but it is the study of specific carbon compounds. Specific carbon compounds, right? Like hydrocarbons. Hydrocarbons are made up of carbon and carbohydrates, proteins, etc. So these all will come under organic compounds, and the study of these specific carbon compounds. So where we study about these things, that is called organic chemistry. And the reason why we are studying organic chemistry or these specific carbon compounds separately, the reason is the carbon can form millions of compounds. Carbon can form a large number, millions of compounds. So in our daily life, we use many organic compounds which are made up of carbon. And these millions of compounds are made up of carbon and some other element like hydrogen, oxygen and nitrogen. And particularly this carbon can form these many a large number of compounds along with other elements. There is a reason for that. Carbon can form these many compounds because of these unique properties. Carbon shows the following unique properties. These unique properties. Let's see what are those unique properties shown by carbon and why it is able to form a large number of compounds. So let's see the unique properties of carbon. Unique properties shown by carbon. Element carbon. First property is carbon's covalency is 4. That means carbon atom always forms 4 covalent bonds. So its valency will be satisfied with 4 covalent bonds. And in the formation of these 4 covalent bonds, the carbon can combine with identical atom, means the carbon-carbon bonding is possible, or it can be the bonding between carbon and any other element like hydrogen or oxygen or nitrogen or sulfur also, and any other halogen. At the same time, carbon can form different kinds of bond like this. It can be a single bond, it can be a double bond, it can be a triple bond. And similarly, carbon can form single chain compounds. At the same time, it can form branched compounds, or it can form cyclic compounds like this. So different kind of compounds the carbon can form. So these many possibilities. So the number of compounds that carbon can form also will increase. So this is the first unique property of carbon element. And the second property shown by carbon is number 2, that is catenation. So catenation is nothing but linking of identical atoms. Linkage of identical atoms to form long chain compounds. Long chain compounds. Like carbon can have a chain with only 2 carbons, or it can form a chain with 3 carbons, or it can be of 4, or it can be 10, or it can be 100, or it can be some 1000 atoms of carbons can combine with each other to form a single chain compound. So this property is called catenation. Catenation means linking of identical atoms to form a long chain compound. So this is a unique property shown by carbon. So there is no other element which can show this catenation property to this extent. So only carbon has that ability to form long chain compounds, even it can have thousands of carbon atoms in a single chain. So this is the second property. Next, third property of carbon compounds is isomerism. So isomerism is nothing but you may have 2 or more compounds, usually organic compounds, 2 or more compounds with same molecular formula, with same molecular formula, but with different molecular different structural formula, different structural formula. So you may have 2 or more than 2 organic compounds where all these compounds may have same molecular formula, but they may differ in their structures. They differ in their structural formula. Okay, so let's see one example. When you take 2 types of compounds like alcohol and ether. Alcohol is one type of organic compound and ether is another type of organic compound. Now let us say a chemical formula, or when you take a compound like ethyl alcohol, its formula will be like this: CH3 CH2 OH. So you can see OH group is attached to this CH3 CH2. Whereas in this case, ether structure will be like this: CH3 bond O bond CH3. So now in this case you can see oxygen between 2 carbon atoms, but here it is with hydrogen atom. But when you count the number of atoms, here it has 2 carbons, 6 oxygens, 6 hydrogens and 1 oxygen. That means this is the molecular formula of ethyl alcohol, this particular alcohol. And if you write molecular formula for this also, even here you have 2 carbons, and 6 hydrogens and 1 oxygen. So when you see this, these are two different structures, these are two different compounds, but they have same molecular formula. That means they have same chemical composition. So even though they have same chemical composition, because they differ in the structures, they will be different compounds. So this property is called isomerism. This property is called isomerism. So what does it say? It may be two or more than two compounds with same molecular formula but different structural formula. So these are the main unique properties of carbon, due to which carbon can form, it is able to form millions of compounds, a large number of compounds. So now in this, let's see the classification of carbon compounds. So here in this case, we mainly discuss about hydrocarbons. Hydrocarbons. So hydrogen represents hydro represents hydrogen and carbon represents carbon. So these are nothing but the compounds which are made of hydrogen and carbon only. Okay, only two elements will constitute these compounds and they are called hydrocarbons. Hydrocarbons are the compounds made of only two elements, that is hydrogen and carbon. Okay, so these are hydrocarbons, and again in this, hydrocarbons can be classified into two types mainly. Hydrocarbons are classified mainly into two types. So one is open chain hydrocarbons and the second one is closed chain hydrocarbons, which are also called cyclic hydrocarbons. So here these cyclic hydrocarbons we don't have in the syllabus, but one example we can learn. That example is benzene. Benzene is a very important organic compound and its formula is C6H6 and the structure will be like this. So 6 carbons will be arranged in the form of a hexagonal ring, and you will have alternate single bond and double bonds between them. Alternate double bond and single bond, and each carbon is bonded to hydrogen atom. Each carbon is bonded to one hydrogen atom. So this is the structure of benzene. So only that one structure or one example we do in this cyclic hydrocarbons, and we mainly focus on this open chain hydrocarbons. So in this again we have two types. One is saturated hydrocarbons and the other one is unsaturated hydrocarbons. Okay, so we are going to see what is a saturated hydrocarbon and what is an unsaturated hydrocarbon. So again this saturated, these are called alkanes depending on the nature of the carbon-carbon bond. And again here unsaturated are classified into two types. One is alkene group and the other one is alkyne group based on carbon-carbon bonding. So mainly we are going to discuss about saturated hydrocarbons, nothing but alkanes, and unsaturated, which are also called alkenes and alkynes. Right? So these are the main hydrocarbons, main types of hydrocarbons we are going to discuss. right? So before we start these three types of hydrocarbons, we see what is homologous series. It is nothing but a series of compounds, a series of compounds, mainly they will be similar in their structural formula. They will be similar in their structural formula, means structures will be similar. Structures of those compounds will be similar, and since their structures are similar, they will be similar in physical and chemical properties. Physical and chemical properties. Okay, but slight variation will be there. So homologous series is nothing but a series of compounds or a set of compounds or a group of compounds where those compounds are similar in the structural formula. They will be similar, or they will have similar structures, and they will have similar properties. They will have similar properties. And in a series, if you take any homologous series, the successive members of the series differ by CH2 group. So we'll see this with example. So first of all, what is homologous series? Homologous series is nothing but it is group of compounds, or it is a series of compounds where they have similar structure. Structure is similar. Because they have similar structure, the properties will be similar. Right? So let's do examples of homologous series, which is nothing but classification of hydrocarbons, we can say. So we're doing together. So first we see alkane homologous series. Alkane homologous series. So in this alkane homologous series, I said the compounds which belong to a particular homologous series, they will have similar structure. So all these compounds, all these alkanes, nothing but saturated hydrocarbons, they will have all carbon-carbon single bonds. Between the carbon atoms, they will have all single bonds. If any hydrocarbon has all single bonds between carbon atoms, then we can call it as homologous series. We can call it as alkane homologous series, or we can call it as alkane or saturated hydrocarbon. Okay, and all these alkenes will follow the same general formula. Okay, they will follow the same general formula, that is CnH2n plus 2. CnH2n plus 2. So this is n number of carbons and 2n plus 2 number of hydrogens. So where you can start n value from 1. N can be 1, 2, 3, 4 and so on. Like this. So this is alkanes. Alkane means all carbon-carbon single bonds. All carbon-carbon single bonds should be there. And they follow a general formula, that is CnH2n plus 2. Okay. Now we'll see alkane homologous series. So now we change the number of carbon atoms and then we write the compounds in that series. Okay. So first we will take n value. When you take n equals to 1, so in that case, what will be the molecular formula when you take n equals to 1, and then the IUPAC name of that compound. Okay, I will tell you what is IUPAC name. Okay, how to write IUPAC name also we learn. Okay, So now first we are taking the n value here. N value, that is nothing but number of carbon atoms. Number of carbon atoms. Now let us take, I am taking n equals to 1. Means I want to take one carbon in the compound. So when you take n equals to 1, the molecular formula will become C1 and substitute n equals to 1. So 2 ones are 2 plus 2. So H4. H4. Similarly, when you take n equals to 2, that is, I am going to take 2 carbons here. So when you take 2 carbons, so accordingly the number of hydrogens will change. So n equals to 2. So 2 to the 4 plus 2. So now it becomes C2H6. So similarly, when you take n equals to 3, substitute n equals to 3, so it will be C3, and accordingly the number of hydrogens will become C3H8. Means 8 hydrogens. Then when you take n equals to 4, this will be C4H10. So this is how we write the formula for each compound of this homologous series. Okay, and now coming to this name, how do we write the name? The name of the compound always depend upon number of carbon atoms. So when you write the number of carbon atoms, depending on the number of carbon atoms, you will have a root word. You will have a root word based on the number of carbon atoms. Plus, now you are writing it for alkanes. So all the alkanes will have a suffix of "ane." Will have a suffix of "ane." Root word plus this "ane." So that will be the name of that particular compound. So let us see the first one. When number of carbons is 1, when you take one carbon, the root word will be taken as "meth." So this is the root word. Meth is the root word for one carbon. So in that case, the name of this compound C1H4 will be meth is the root word and ends with "ane." So that is methane. Methane, that is CH4. And when n equals to 2, the root word will be eth, ETH. So in that case, root word is eth and always end with "ane." So this is ethane. Okay, C2H6 is ethane. Now for 3 carbons, prop. So then in that case, the name of C3H8 will be propane. And for n equals to 4, for 4 carbons, it is but. Then the name of C4H10 will be butane. Butane. So this is how we write the name for alkane homologous series. So this is alkane homologous series and they are saturated hydrocarbons. So next one we see another homologous series that comes under unsaturated hydrocarbons. Unsaturated hydrocarbons, again they are classified into 2 types, alkenes and alkynes. Okay, so second homologous series is alkene homologous series. Alkene homologous series. So this will also comes under unsaturated. Alkene, alkyne, both will come under unsaturated hydrocarbons. Okay, alkene also unsaturated hydrocarbon. And when you are taking alkanes, all carbon-carbon bonds should be single bonds. All carbon-carbon bonds should be single bonds. In case of alkenes, there should be at least one single bond. Okay, there should be at least at least one single bond. One single bond. At least one single bond. It can be more than one also. At least one, sorry, at least one double bond. At least one double bond. At least one double bond between carbon-carbon. Means between two carbon atoms, there should be at least one double bond. Then we call it as an alkene or unsaturated hydrocarbon. And alkenes also have a general formula. Again, we are talking about simple alkenes. Simple alkenes will have a general formula CnH2n. Means for n number of carbons, there will be 2n number of hydrogens. Okay, so let's write the homologous series of this. But here n starts from 2 because with single carbon atom you cannot show double bond between two carbon atoms. To show two bonds between two carbon atoms, you should have at least two carbons. With single carbon it is not possible, so it starts with two carbons. Right. Let's draw the table. So first we are taking number of carbon atoms, that is the value of n. Then the molecular formula of the compound. Molecular formula of the compound following this. Then the IUPAC name. IUPAC name. So in this also similar thing, we'll write root word corresponding to the number of carbon atoms plus these are alkenes. These are alkenes, so it will end with ene. So like this we draw the table. Now as I said, you have to take at least two carbon atoms. So two carbon atoms, root word will be ith. And for 3 carbon atoms, n equals to 3, root word will be prop. So this remains same. For 1 carbon meth, 2 carbons ith, 3 carbons prop, and for 4 carbons, that will be root word will be but. So when you write the formula here, n equals to 2 you are substituting, this will be C2H4. And the name will be for 2 carbons ith, and we are writing enes, ethene, and for 3 carbons it is C3H6 and this is propene, and for 4 carbons it is C4H8 and this is butene. Okay, eth represents 2 carbons, prop represents 3 carbons, but represents 4 carbons. So that it will remain same, root word remains same every time, means depending on the carbon atoms. Right, so this is about alkene homologous series, which comes under unsaturated hydrocarbons. And next unsaturated hydrocarbon, that is alkyne. Next one, alkyne homologous series. Alkyne homologous series. Okay, so alkynes will come under unsaturated hydrocarbons. Unsaturated hydrocarbons. If it is alkene, there should be at least one double bond. Enes will have double bond. Anes will have all single bonds. Now ines will have at least one triple bond. Okay, alkynes will have will have at least one triple bond. One triple bond. It can be two triple bonds or three triple bonds, but we are talking about simple. At least one triple bond is there, then we can call it as an alkyne. Right? And alkynes also will follow a general formula. A general formula, that is CnH2n minus 2. Okay, so this is a general formula. So for n number of carbon atoms, there will be 2n minus 2 number of hydrogen atoms. So let's write the table for this also. So first we are taking number of carbon atoms, then this is value of n, then the molecular formula we follow this, just substituting the n value, and the IUPAC name. Here also we'll write root word plus, now these are ines. Okay, so root word plus ine. So this is IUPAC name. Right. So when you take n equals to 1, every time when you, here also what happens? It should have at least one triple bond. So when it is at least one triple bond between two carbon atoms, you have to take at least two carbon atoms. With single carbon atom, cannot show it is an alkyne. At least two carbon should be there. So here also we start with n equals to 2, and the root word will be ith. And when you substitute n equals to 2 here, C2, 2 to the 4 minus 2, C2H2. And its IUPAC name, for two carbons, root word is ith. So ith, and it ends with ine, ethyne. And for n equals to 3, same root word, that is prop. Every time when you have 3 carbon atoms, it is prop. And this will be C3, substitute 3 value, n value 3, 2 3 are 6 minus 2, 4, C3H4, this is propyne. Similarly, n equals to 4, so this is, root word is but, formula will be C4H6, C4, 2 4s are 8 minus 2, C4H6, and the IUPAC name will be butyne. So it goes on like that. So this is how we write the homologous series of alkynes. So let's write one more compound with n equals to 5. When you take n equals to 5, the root word will be pent. Root word will be pent, and the formula will be C5H8. N equals to 5 we are taking, so C5, and when you write n equals to 5, 2 5s are 10 minus 2, 8. So C5H8, and the name of this compound is pentyne. Pent represents 5. Here 5 carbons. Right. So this is about homologous series and the classification of hydrocarbons. So we have done them together. Right. So next very important topic is isomerism. Right. So in this you will have two types of isomerism. In our syllabus we have only two types. One is chain isomerism, and the second one is position isomerism. Okay, So two types of isomerism we are going to discuss. So first we do what is chain isomerism. So this chain isomerism, this is due to, chain isomerism is due to the difference in the arrangement of carbon atoms. Arrangement of carbon atoms in the chain. Okay, so this chain isomerism, this property arises when there is a difference in the arrangement of carbon atoms in the chain. Let us say I have a formula C4H8 or C4H10. So this is the formula I have. That means I have to make a compound with 4 carbons and 10 hydrogens. Now there are two possibilities. One, I can put all the carbons as a straight chain, or 3 carbons as a single chain and 1 carbon as a branch. 1 carbon as a branch. And I already told you the covalency of carbon is 4. Carbon always forms 4 bonds. So that is compulsory, you have to remember. And with 4 carbons, I can make this structure or I can make this structure. And remaining bonds to be filled with hydrogen. So when you fill these empty bonds with hydrogen, so exactly you will get that formula C4H10. In the same way here also, if you fill the remaining bonds, so here also you will get the same formula C4H10. You can count here, there are 4 carbons and 10 hydrogens. Okay, so both have same molecular formula, that is C4H10, but they are different compounds. They are different compounds. So this is a different structure, this is a different structure. So this is called isomerism. See, the structures are different, so different compounds, but the molecular formula is same. So this is isomerism, and this isomerism is because of what? Because of or due to the difference in the arrangement of carbon atoms in the chain. So this is called chain isomerism. And since I have 4 carbons, so these two structures are possible. If you have the number of carbon atoms increasing, the number of the structures, possible structures also will increase. So those are called isomers. These structures are called isomers. So for this particular example, I have 2 isomers. If I take C5H12, it will have 3 isomers because number of carbon atoms increased. So if you take 6 carbons, so it will have more than 3 isomers. So as the number of carbon atoms increase, the number of isomers also will increase. So just remember, chain isomerism is due to the difference in the arrangement of carbon atoms in the chain. So this depends upon how the carbon atoms are arranged. Okay, so they can be arranged in this way or they can be arranged in this way. Here is only single chain, here there is a branch also. So this is because of chain isomerism. Right. So next one is position isomerism. So this is due to the difference in the position of a substituent. We'll see what are the substituents in the position of substituent or functional group or double bond or triple bond. Okay, so this is the difference in the position. Difference in the position of what? It is the difference in the position of the substituent or it can be a functional group, or it can be a double bond or triple bond. Okay, let's see an example. For position isomerism, in position isomerism, you will not see any difference in the arrangement of carbon atoms, but you will see the difference in the position of the substituent or functional group. So, for example, if you take a formula C3H5, C3H7OH. So this is the formula I have: 3 carbons, 7 hydrogens, and 1 OH group. Okay, so I am taking carbons. So here I am not showing any difference in the carbon chain. If I show some difference in the carbon chain, that will become chain isomerism. But we are talking about position isomerism. So here there is no difference in the chain. But what is the difference here? There is OH here. I can have OH either on the first carbon, or I can have OH on the second carbon. And remaining empty bonds we fill with hydrogen as it is. So you can have the same formula C3H7OH. Even here also you will have same formula C3H7OH. See here, both are having same formula C3H7OH. C3H7OH. This is also C3H7OH. But they are different compounds. Why they are different compounds? Because the position of OH is different. The position of OH is different. So they are two different compounds. Or it can be, this is the functional group, at the same time we can call it as a substituent. Okay, or it can be position of the double bond or triple bond. So let us say I have a formula like this, C4H8. So by looking at the formula we can understand. So this is as per the formula CnH2n. So which represents alkene homologous series. So this should belong to alkenes, means there should be a double bond. So in this case I can have two types of structures. So first, so carbon chain there is no difference, but since it is an alkene there should be one double bond. Since it is an alkene there should be one double bond. So I can have double bond on the first carbon, or I can have double bond on the second carbon. So remaining will be single bonds. Remaining will be single bonds, still it remains alkene, unsaturated hydrocarbon. And if you fill the remaining bonds here, you will have the formula C4H8. So you can count the number of carbons and hydrogens here. It will be C4H8, and even here this is also C4H8. But the difference is the position of the double bond. Here the double bond is between first and second carbon, but here the double bond is between second and third carbon. So here this isomerism is due to the difference in the position of the double bond, or it can be triple bond also, or it can be a functional group or a substituent. Okay, so these are called position isomers. These two are position isomers to each other, and these two are position isomers to each other. Okay, so this is about isomerism. Isomerism means two or more compounds may have same molecular formula, but they will have different structural formula. Okay, and in this we have two types. One is chain isomerism and the second one is position isomerism. Right, next we start IUPAC nomenclature. IUPAC nomenclature. Okay, so here nomenclature is nothing but naming an organic compound. We are naming or giving a name as per IUPAC rules, as per IUPAC rules and instructions. So this IUPAC is nothing but International Union for Purified and Applied Chemistry. Okay, so this is the full form of IUPAC. So usually this won't come like what is the full form of IUPAC, but just for information, this is IUPAC. Okay, and so as per this international union, they have set some rules. Okay, so they have set some rules how to name a chemical compound. It can be an organic compound or it can be any other compound. So here we are discussing about organic compounds, how to name organic compounds. Right. So in this IUPAC nomenclature of organic compounds, mainly you will have two parts. A root word. Already we have seen what is root word. Root word depends upon the number of carbon atoms. Plus primary suffix. Primary suffix. Primary suffix is nothing but, already we have written an, in, ein. Primary suffix is nothing but an, in, ein. So it can be an or it can be in, it can be ein. So it mainly depends upon what kind of bonding is present. Okay, and these two are compulsory. So these are basic name for an organic compound. And apart from that, you will have a secondary suffix if there is any functional group. If there is any functional group, you will write secondary suffix. Otherwise, if there is no functional group, there is no secondary suffix. The secondary suffix only represents the functional group. And if there is a branch or a substituent, then you will write a prefix. So this prefix represents a substituent. This represents a substituent. So these are the main four parts of IUPAC nomenclature, right? So where these two are primary, basic. Okay, so these two are definitely there for any compound. If you have any functional group, then you will add secondary suffix. If there is any substituent, you will add prefix. Otherwise, you don't add this prefix and secondary suffix. Okay, right. Now, in this case, let's see what is the root word depending on the number of carbon atoms. Okay, so if you have one carbon, the root word will be meth. Already we have seen this. If two carbons, root word will be it. If three carbons, root word will be prop. If four carbons, root word will be but. If five carbons, root word will be pent. If six carbons, root word will be hex. So up to 6 carbons it is compulsory to learn. Compulsory to learn. And this is primary suffix. If all single bonds, then it is ane. Single bonds we are talking between carbon and carbon. Between carbon and carbon, if all single bonds, we write primary suffix as ane. If at least one double bond is there, the secondary suffix will become ene. If at least one triple bond is there, then the primary suffix will become ine. So this is the table for the primary suffix and the root word. And coming to the functional group. So we are discussing only about 4 functional groups. That is, if you have carboxylic acid group, carboxylic acid. So this is the structure COOH. If this COOH is there, then the secondary suffix is added only if there is a functional group. Okay, and if that functional group is carboxylic acid, means if that functional group is COOH, then you will add oic acid as the secondary suffix. In case if you have aldehyde, that is CHO, then you will add just 2 letters Al, only 2 letters Al. And if you had ketone group where you have carbon with double bond O and both the sides carbon, so there you will add ONE. We pronounce it as on. And last one, alcoholic group, that is OH. If alcoholic group is there, you will add OL. Okay, so this is about the functional group. Okay, then finally prefix. Prefix is added only when there is a substituent. If there is any substituent, then you will add this prefix. So what can be those substituents? We'll see here. The substituents will be, so in our syllabus we have Cl. If Cl is present as a substituent, then the prefix is given as chloro. If it is bromine, it is bromo. If it is iodine, that is iodo. If it is CH3, this is methyl. CH3 is methyl. And apart from that, if you have 2 substituents, we will write di. If you have 3 substituents, we write tri. If you have 4, then tetra. Okay? Means identical substituents. If you have 2 chlorines, we write dichloro. If you have 3 chlorines, you will write trichloro. If you have 4 chlorines, you write tetrachloro. Similarly, dichloro, trichloro, tetrachloro. Similarly with methane. If you have only one methyl group as a substituent, we write methyl. If you have 2 substituents of methyl, we write dimethyl. We'll see examples. When you see examples, it will be clear. Right. So let's start some examples for writing this IUPAC nomenclature. Okay. So example 1. Let us take this compound CH3, CH2, CH3. Right. So in this case, you can see 3 carbons, and all these 3 carbons are in a single chain. Okay, there are no branches, no substituents. Okay, no substituents means no prefix. And you can't see any secondary suffix, means no functional group. There is no COOH, there is no CHO, there is no CO, there is no OH. So for this particular compound, it is a simple organic compound. It is a simple organic compound. So you will write only the root word and the primary suffix. So how do we choose the root word? How many carbons are there? 1, 2, 3. For 3 carbons, root word is prop. So this is prop. And what should be the secondary primary suffix? An, in, I. If all single bonds, you will take an. So these are all single bonds. So this is propane. This is propane. Or we can write N-propane. That N represents, it is a simple saturated hydrocarbon. Okay, so there is no substituent, there is no functional group, nothing. We just writing root word and primary suffix. And we just add small n before that, representing it is a small, means it is a simple hydrocarbon. So this is example 1. Next, example 2. Let us take this compound CH3, CH3Cl. Now you can see there is a substituent there. There is a chain of carbons. There is a carbon chain, and on the carbon chain you have a substituent. So this becomes a substituent now. So chlorine is a substituent. It is a substituent. Okay. So forget about the substituent. First you have to write the name of the main chain. So first, whenever you write the UPSC nomenclature, first you have to choose, you have to find the main chain or the longest chain. So in longest carbon chain. So this is the main carbon chain. So first you have to name this. Forget about the substituent. So in this main chain, 3 carbons are there. 1, 2, 3. For 3 carbons, again same prop. And here you have single bonds. In the chain you have single bonds only. For all single bonds, it is N. So now primary root word is done, primary suffix is done, and luckily we don't have any functional group, so there is no secondary suffix. But for this substituent, you have to give the prefix. What is the prefix? Chlorine, chloro. So this is chloropropane. But when you are writing the substituent, you have to show the position. You have to show the position of that substituent. So position means to which carbon this is attached. So this chlorine is attached to the second carbon. So this is the first carbon, this is the second, this is the third carbon. So chlorine is attached to the second carbon. So this will be 2-chloropropane. That number 2 is the position. That number 2 represents the position of the chlorine. You do be clear about that. Right. So next example, example 3. Let's do this. CH3, CH3, chlorine and chlorine. Okay, let's try this. Okay, let's try the name of this compound. So here also first you have to look for the longest carbon chain or main carbon chain. So in this you have to name that first. So how do we name? See how many carbons are there. 1, 2, 3, 4. So for 4 carbons, root word is but. So this is but, and all single bonds. So this will be N. Okay, so that is butane with two chlorine substituents. Chloro. For chlorine we are writing chloro. But how many chlorines are there? Here one, here one. Two are there. So when you have two identical substituents, you will add this prefix dichloro. But again, the position of these two is compulsory. So both chlorine atoms are not on the same carbon. Both are not on the same carbon. One is on the second carbon, the other one is on the third carbon. So if this is first, second, third, fourth. So you have to show the position 2, 3. 2, 3 dichloro. Di means two chlorines. Two chlorines are present on butane. And where are they present? On the second carbon, and one on the second carbon and another on the third carbon. So that is 2, 3 dichloro butane. Right. Next. Example 4. Let's try this. CH3, CH2, CH2, CH3, and you have CH3 here. Okay, let's try the name of this compound. Okay, so now in this is CH3 the substituent and this is the main chain. Okay, that is the longest carbon chain. So let's name this carbon chain first. Okay, so in this 1, 2, 3, 4, 5, 5 carbons are there. For 5 carbons it is pent. It is pent. All are single bonds, so pentane. But you have CH3 on the second carbon. So how is it second carbon? In this case, you have to start numbering from right side. Okay, so numbering is given in such a way that the substituent's position will be getting the least number. Okay, so if you give numbering from right side, CH3 will be on the second carbon. If you give numbering from the left side, 1, 2, 3, 4. So CH3 will be on the fourth carbon. So between second and fourth, which is the least number? 2 is the least number. So we always give numbering in such a way that the substituent will get the least number, least position. So now it is on the second carbon. So 2 methyl. That 2 is the position. That is not the number of methyl groups. That number 2 is the position. Methyl group is on second carbon. That is the position. 2 methyl pentane. Okay, right. Next example, example 5. Example 5, CH3, CH2, CH double bond CH2. Okay. Let's try the name of this compound. Right. So in this, you have only one main chain which has 4 carbon atoms, and for 4 carbon atoms, the root word will be but, and now you have a double bond here, not all single bonds. When you have at least one double bond, so this becomes ene. But you have to show the position of the double bond. You have to show the position of that ene. Where is that double bond present? So in this case also, you have to give numbering in such a way that the double bond, triple bond or substituent or functional group, whatever it is, that should get the least number. So here we consider this is on the first carbon, so this will be but1ene, or you can bring this one to the front. So it becomes 1-but-ene. So we can write it as but1ene, or you can write it as 1-butene. So both are correct. And let's do the last example in this case. With functional group, we'll do one example. So next example, example 6. Right, when you take CH3, CH, CH2, CH2, CHO and Cl. So now in this case, you have both the functional group as well as substituent. Where is the functional group? CHO is the functional group, means this aldehyde group is there. And Cl is the substituent. Chlorine is the substituent. Okay, so forget about the substituent. First you have to take the carbon chain, including the functional group carbon. You have to include that functional group carbon also. So in this you have how many carbons? This CHO. How many carbons are there? 1, 2, 3, 4, 5. So for 5 carbons, root word will be pent. And these all are single bonds. So pentane. And you have a functional group here. So this CHO. For CHO, you have to add a secondary suffix. Means after the primary suffix, after this ane, you have to add the secondary suffix. What is the secondary suffix for CHO? Al. But when you are adding Al secondary suffix, you have to remove this E and then add Al. So that becomes pentanal. Right? So whenever you add this secondary suffix, you have to remove the E. Remove the E from ane, ene or ine. Then you have to add the secondary suffix. Then as usual, you have to give numbering. But when you have functional group and substituent, you have to give preference to the functional group. So first preference has to be given to the secondary suffix. That means you have to give numbering such that the functional group gets the least number. Okay, you have to give numbering such a way that the functional group gets the least number. So if you give numbering from here 1, 2, 3, 4, 5, this is getting number 5. If you give numbering like this 1, 2, 3, 4, 5, so that is getting number 1. So which is correct one? The way in which it gets the least number. means here 1, 2, 3, 4, 5. You have to give preference to the functional group when you have functional group and substituent both. Okay, so now this is 1-al, or for aldehydes and carboxylic acids, if you don't mention that one also, it's okay, because CHO and COOH always on the first carbon. But position of chlorine, it is on the fourth carbon, 4 chloropentanal. So it becomes 4 chloropentanal. So this is on the first carbon. Aldehydes and carboxylic acids will be on the first carbon itself. They cannot be anywhere else. Right? So there it is not compulsory to put 1 here. Even if you put 1, it is not required. Okay, 4 chloropentanal. So this is the name of that compound. Okay, one more example we'll do in this case. Example 8. Simple example we'll do. CH3, CH, CH3, OH. Okay, so very simple compound. And OH is alcoholic group. OH is alcoholic group. So in this, you have this chain with 3 carbons. For 3 carbons, it is prop, single bond, single bond. So in the chain, you have all single bonds. When all single bonds, we write N. And you have a functional group. What is that? Alcoholic group. Alcoholic group, you have to write OL. But before that, you have to remove this E and write OL. But this OH can be anywhere. So it is compulsory to write its position. It is on the second carbon. So it will be prop-N2-ol. Prop-N2-ol. Or you can bring this 2 to the front. So the name you may write as 2-propanol. 2-propanol. Okay, right. So for today, we end the class here. We'll continue in the next class. So next class we discuss how to write the structures and the preparations of organic compounds. So that will be discussed in the next class. I hope you understood these topics. Right. Good night. Bye.